Alright, looks like we're live. Hello everyone and welcome to yet another Zoisin session. How about that? How about that? Bet you didn't expect that shit to happen. Let's make a little bit of an announcement on our Discord server. So we're currently live on Twitch, if I'm not mistaken, right? Live on Twitch. And what are we doing today? We are programming in Rust. We're programming in Rust, specifically we're implementing persistent stack, which is rather interesting. We get to what it is a little bit later. So https twitch.tv/zodding, and we're gonna ping everyone who wants to be pinged, and there we go, the stream has officially started. Hello everyone, hello, welcome. Chat, tell me, what do you think about Rust? Anyway, so what is a persistent data structure? Right. So specifically we're implementing persistent stack, but generally there is like a whole class of data structures called persistent data structures. So let's actually Google it up. Persistent data structure. Right. I'm going to prepare the description because I want to put the link about this thing in the description as well. In computing, a persistent data structure, or not ephemeral data structure, I never heard like the term ephemeral data structure, to be fair. I only heard persistent one. It's a data structure that always preserves the previous version of itself when it's modified. That is very interesting. So, specifically, quite often the persistence is applied to trees and stuff like that, but we're gonna apply it to stacks, specifically linked lists. So I really want to give the link to this thing in the description, but if I just copy paste this entire stuff, it will contain some garbage that Google put in there, put in here. I don't know what's going on with my speech today. So I have to specifically remove all of that. This kind of stuff is so annoying. I don't know why Google keeps doing that, and it's so difficult to get rid of that. And it's just like, oh, they think it's helpful, but it's not helpful at all. It's just like puts a lot of garbage in your URL, and if you want to share something, it's just like you have to do this extra work of removing all of that. It's just so annoying. I don't know. Anyway. So, okay, so why do we even need a persistent data structure? So, believe it or not, this entire stream is actually related to Porth, right? So, I've been developing my own programming language called Porth for like more than 2 months already, I think. Right, so I'm gonna give the link to this language here in description. If you're watching live, I'm going to put that in the chat. So here it is. You can find it in here. So Porth programming language. Right. Here's the Porth programming language. And it's a stack-based programming language, meaning that all of the operations, like literally everything, is done via the data stack, right? So we can take a look at some of the examples of this language soon. Chirurgical, thank you so much for 29 months of Tier 1 subscription. Thank you, and welcome to our epic Rust Club. Okay, so let's take a look at some example. Brainless Jellyfish, thank you so much for 2 months of Twitch Prime subscription. Thank you, and welcome to our epic Rust Club. It's not a Rust Club yet, it's still a Porth Club, but after we're done with Porth, we're gonna do some Rust. Bineber18, thank you so much for 2 months of Twitch Prime subscription, and welcome to our epic Porth Club. Okay, so let's take a look at Hello World. Right, so hello Porth. Okay, Emacs, what is going on? Hello Porth. There we go. So I need to include the standard library, right, and then I don't think Hello World is actually a pretty good example of this, you know, stack orientedness of the language. So let's actually do something like a thing that sums up 2 numbers. So if you type 34, that is a command within the language to put that number onto the stack. Right, if you type another number, it will put another number onto the stack. Right, and then you have operations that operate on the top elements on the stack, like plus, right? So this thing takes top 2 elements on the stack, sums them up, and puts the result back on the stack. And here, at the top of the stack, after this plus operation, you're going to have the sum on the stack, and then you can do print, and that thing will print the result of the sum to the screen, right? So I think we don't need this tiny library for that, so this is a very simple program. And if I try to compile and execute that program, it is going to print 69, right? As you can see, it compiled this entire thing and printed the result. Okay, that's pretty cool. So this is what it means for a language to be stack-oriented, right? If you want to learn more about stack-oriented languages, I really recommend to just Google up that term, or specifically Google up Forth. I think this is the most prominent stack-oriented language, right? A lot of people get into the stack-oriented paradigm by looking into Forth, so I really recommend to check it out. So I'm gonna put the link to the Forth Wikipedia article in the description as well, just for anyone who's interested. Okay, one interesting thing about Porth is that it is statically typed, right? It is statically typed. So essentially, during the compilation, the compiler actually checks that you're not trying to do things that you're not supposed to do. For instance, here, for a plus operation to actually work properly, you need to have at least 2 elements on the stack, and this is ensured by the compiler. For instance, if you remove one of the elements, this is not going to compile, because the compiler cannot prove that you have enough elements on the stack, so it will tell you not enough arguments for the plus operation. So if you try to compile this entire thing, basically it will tell you that. So it tells a lot of things in here, and this is because the plus operation is overloaded, right? It can sum up integers, it can sum up pointers and integer endpoints and stuff like that, and basically for each overloaded plus operation it tells you that you've got an error. So the entire error reporting is not really well, you know, polished. So I just hacked together something just for the compiler to report, so it's not really that important. But in any case, it just tells you that there is not enough arguments for the plus, right? And yeah, so that's basically it. And interestingly enough, this static type checking actually works for if conditions, right? So for instance, what we can do in here, for instance, we summed up these 2 numbers and then put 69 onto the stack, and we compared, and this entire thing will give us Boolean, and we can dispatch, we can basically do a conditional check on upon that Boolean, right? So the execution will go here if this condition is true, and it will go here if this condition is false, right? So you can even do something like true, and you can print this thing onto the screen, and then you can do false, and you can also print that onto the screen. So just a second, I think I forgot about a very important thing in here. I forgot to put something behind my camera, right? So I usually just put some sort of a window behind my camera, just in case I actually start typing somewhere where you can't see. Right, so it just makes it easier for me to know whether you can see what I'm typing or not, so it's pretty convenient. Okay, so, and what's interesting is that our type checker is capable of even checking this kind of stuff. Right, so yeah, so we can even remove puts, and we can put puts in here, right, and the compiler will check that both of the branches put enough arguments for the puts to consume. Right, so here's the very important. So if one of the branches don't have enough arguments for puts to consume, right, so the program may work only when this condition is true. But when this condition is false, there will be no arguments for this thing, so it will crash, or, you know, yeah, it will basically crash and segfault. So our compiler will ensure that in both of the branches you have enough of the arguments for this operation. Right, so if I try to do something like this, it doesn't have puts because it's located in the standard library. Right, it is located in the standard library. So, and as you can see, it just says true. If I compare it with 70, it will say false. Right, but if in one of the branches you don't have enough arguments for the puts to consume, this will not compile, and it will explicitly say not enough arguments provided for puts, right? So, and then you'll have to go and fix one of these things. So the question is, how does it do that? Marilla, thank you so much for 10 months of Twitch Prime subscription. Thank you, and welcome to our Epic Porth Club. So, the way it does that, right? So the way it type checks the program generally. During the compilation, it maintains the type stack, right? During the execution, we have the data stack where you put the data that you operate on. But during the compilation, we have a type stack. And what the program does, it just goes through each individual operation and just puts the data type of this thing onto the type stack. Right, and then checks if the types match together, right? So when it encounters 35, it will put integer onto the stack, then another integer onto the stack, then it will encounter plus, and it knows that plus consumes 2 integers, so it will look at the type stack, see 2 integers, and say, okay, that's type checks. That actually type checks, so everything's fine. So, and when it encounters if, something interesting is happening. It splits the stack in 2, right? So essentially it has an execution context, which has its stack of the types and stuff like that. And if it encounters if, it splits the entire context and continues the type checking in 2 contexts simultaneously. So basically it will type check the execution if it goes here, and then it will type check if the execution goes here. And then both of the executions will merge together in here, right? So basically what we do like a small BFS on the control flow of the entire program, right? We BFS the entire control flow of the program. So for those who doesn't know BFS, it's a algorithm on graphs. So yeah, essentially you have a graph, or like in our case, it's a tree. I think, yeah, it's actually a graph. It's a directed graph. And you basically sending a wave through that graph, like this. Here's the wave going on, and that's basically what we're doing. We're just basically sending a type checking wave through the entire program, right? That requires, again, as I already said, copying the stack, copying the execution stack. And we can even take a look at how it's done in the Python program. So type check, I think it's somewhere here, type check program. Type check program, so here is the execution context, right? I think it's here. Yeah, there we go. So we have a variable called context, which is a list of contexts, right? And we start with a single context, which starts at the instruction 0. And as we go further and further, when we encounter ifs and maybe if stars and maybe while and stuff like that, well, while doesn't split anything, do splits, we actually copying the entire context. We create a new one, which copies the stack, copies some other like expected outputs of the execution. So this is just details, but you see there is like the situation of splitting the stack and stuff like that. So in Python, it's relatively easy to implement because Python is a dynamic, garbage collected, and so on and so forth. But we are currently re-implementing Porth in itself, right? And Porth is closer to assembly than to scripting language, right? So essentially we don't really have any automatic memory management, and just copying stacks around is kind of tedious and kind of like error prone. So what I was thinking is that we need to develop a data structure and approach where doing this kind of stuff in such a low level language would be easier, right? You see what I'm talking about? So essentially, like, type checking requires like, you know, sophisticated algorithms and data structure. They're not that sophisticated, but you have to implement them in a low-level language, right? And we need to come up with something that is easier to manage, right? We need to come up with something that is easier to manage, right? The idea that I have in my mind is some sort of like a persistent data stack, right? Persistent type stack, right? Because we're operating on the level of types. So, and that could be achieved by implementing the stack using linked lists, right? So, which is rather interesting. So I'm going to show you. Let's actually open up my Paint. And in my Paint, I'm going to show you what I mean. Okay. Let me try to do this thing. So essentially, how do you implement a stack using linked lists, right? So essentially you create a bunch of nodes, right? So when you push a 1, you create a node that puts 1 like so. I think I need to switch this entire thing, right? So here's the first element on the stack. Then you want to push 2 onto the stack, right? You create a new node, you link the previous thing to 1. The previous thing for a 1 would be null probably, right? And the top of the stack is going to be here. So here is the top of the stack. So you have 2 elements on the stack. And then if you want to put 3 on the stack, you create a new node and you link it with the previous one. Here is your new top. And this is how you implement stack with linked lists. If you want to pop an element from the stack, you essentially look at the top, you follow its previous element and you set the new top in here and you do something with this node. You forget it if you're working in a garbage collecting language. You remove it manually if you work in manually, manually managed language, and so on and so forth. So this is basically how you do that. So what's interesting is that this kind of approach makes it super easy to copy and split the stack in two. So let's actually reorient the stack a little bit. Let's actually orient it like vertically. I also want to just make it a little bit more saturated, if you know what I mean. So I'm just trying to find a good color for this entire thing. I think this is a good color. Okay, so imagine that you're pushing some stuff onto the stack, right? So we have 1. So this is basically the first element in the stack. This is null. Then you have 2, right? And then you have 3. And then at this point, you decided you want to split this stack, right? So your top is currently pointing here. And at this point, you want to copy the stack and just split it, right? So what you do, you keep this top as a separate pointer, and then you create a new pointer, right? And you put something like 4. Right, so maybe I want to choose a different color. Let's actually choose like a red one or like a pink one. So this is a 4, and you have 2 stacks in here. So one stack pointing here and another one pointing in here. Right, and then you decide that you want to put an element into the green stack. Right, in that case, you would do something like this. So this is going to be 5, and basically, you're gonna have this node that is shared between 2 stacks, right? So the first stack is here, right? If you follow down, here is the stack, and if on the second stack you have this stack, and they sort of share like a part. They sort of share a part. So when the elements of these stacks are shared, it's kind of dangerous to just like blindly remove them, right? So if you start popping elements out of the stack, you can't really remove elements that are shared. So in our case, we probably want to forget them, right? So imagine that you want to pop an element from this thing. So you basically go into follow and make this thing your new top, and you're basically going to forget this thing, right? Then you decide, okay, let's actually pop another element out of this thing, and this is going to be our new top. And then you decide, okay, I want to push a new element in here, right? I want to push a new element in here, so I'm going to put it here. So this is going to be something like 6, and this is my new top, right? So you have 2 stacks in here. The first stack starts somewhere here, and the second stack starts somewhere here. So here is the first stack, and here's the second stack. And this basically becomes an unreachable node, right? This becomes an unreachable node. But you quite easily can copy this entire thing. So it's super easy to implement something like that in a low-level language where you just like create and link the nodes, and you don't have to copy like chunks of like memories and stuff like that. You just like pile things on top, and it makes it super easy. So the question is, what do we do with sort of like a leaked node? Is everything clear so far, by the way? Because I'm not sure if I make any sense, right? Is everything clear what I'm trying to say? So is there something like, yeah, so you have this approach where you can just pile and leak the nodes, and don't get scared of the idea of leaking nodes, right? I know that I have a lot of CS grads in the chat who are super scared about leaking anything, right? Because it's super dangerous, because their professor is gonna like punish them for that, right? But here there's no your professor in here. Trust me, it is okay to leak a little bit of memory. It is totally okay to leak a little bit. As long as it doesn't consume your entire memory, it's okay to do that. Anyway, it's 2021, just buy more RAM. Exactly, that's exactly what I'm talking about. So here's an interesting thing. We can basically pre-allocate a fixed amount of nodes. So usually when I work with like trees or linked lists and stuff like that, the things that have fixed size nodes, right? They have I'm reading your nickname and I'm trying to say thick ogre, right? Fixed, thick size nodes, yes. Thick ogre, thank you so much for Twitch Prime subscription. Really appreciate it. Okay, so usually, when I'm working with a data structure with a fixed size nodes, I like to pre-allocate a fixed amount of such nodes, right? So I like to pre-allocate like an array somewhere in the static memory, right? Somewhere in the static memory. Thank you so much, Damis VE, for Twitch Prime subscription. So maybe I want to actually make this entire thing a little bit thicker so you can see. So here's what we have, and each of these elements of that array is going to become a node that you can use for building this data structure, right? So, and essentially I would implement a simple like bump allocator on top of that array. Every time I need to allocate a new node, I will just grab this node and move the pointer to the next thing, right? So I move it in here and then allocate another one and then move it in here and so on and so forth. So that way I just like linearly like, you know, allocating these nodes. And within these nodes, you can refer to other nodes via the pointers and stuff like that. So basically this entire data structure can be linearly stored in some sort of like a global array with fixed pre-allocated nodes, right? And that way I'm basically allocating the nodes myself. Right, and here's an interesting thing. As I already said, this entire approach is leaking the nodes, right? It is leaking the nodes. But maybe for our type checking process, it is okay to leak them. Right, maybe our type checking process is not going to produce that much of a waste, right? It doesn't produce that much of a waste that it will be okay if some of these nodes are leaked, right? And if there's not enough nodes, for the time being, we can just basically allocate bigger buffer. And as we get to some, you know, stable point, we can implement like a dynamic growing thing in here that basically like grows as you need more and more nodes, and you don't have to deal with the fixed ones. But maybe it's not going to be okay. So we'll have to somehow estimate how much waste our type checking process produces. And if it does produce waste that we want to clean up, how are we going to clean up sort of like these leaked nodes, right? How are we going to clean up this, you know, leaked nodes? So I think we can implement a more sophisticated allocator in here, right? We're not gonna only like bump allocate things, right? We want to be able to free the nodes, right? We need an ability to free the nodes since we don't need them. How I usually do that? Usually I create a second array where I keep track of the freed nodes, right? So essentially I allocated a bunch of nodes in here, and then I want to free this one. Before freeing this one, I will grab its index. I'm gonna put it in the array of free nodes, right? So I know that this thing is free and this is in my list. And the next time I need to allocate a node again, instead of like bumping these nodes, all right, allocated nodes, I will just look at the array of free nodes and grab the one by index 2 and reuse it. Right. So basically by adding another array, we have an ability not only allocate nodes, but also free them. Right, and then later reuse them. So it's a very simple allocator, right? Implementing an allocator for fixed-sized objects is actually super easy. It is difficult to implement an allocator for objects of variant size, right? As a matter of fact, I think I made like a series of videos on that on my YouTube channel. I'm pretty sure I did. It's something about writing your own Malloc and free, and also writing your own garbage collector and stuff like that. So I really recommend to check it out. So let me see. Sodding Malloc. Let me see. So writing your own Malloc in C. Right, I really recommend to check this out. I think that stream was actually very interesting. I really enjoyed doing it. Okay, so I'm gonna put that thing in the description. So writing my own Malloc in C. Right, but here we were trying to implement an allocator for like a variable size object, which is rather difficult to do fast. Here we have an allocator for a fixed sized object, which is super easy. You just have two arrays. The first array is pre-allocated objects, and the second array is the index of free objects that you can reuse in the future. It makes it super easy. Okay, so we have an ability to allocate nodes for our weird data structure, and we have an ability to deallocate them. But the question is, how do we even detect that some of these nodes are leaked? Right, because we cannot just deallocate nodes as you pop them, right? Because if you have a stack in here, you pop this thing, you deallocate it, okay, but now you're pointing in here, and now you pop again and you deallocate this thing, but this thing is pointed by this stack. Right, so you have to be careful. You cannot just like blindly deallocate nodes, right, which can be like reused by other things. So we could take an approach of reference counting. As you can see, we can clearly see that that node is actually pointed by two things. But here is an interesting thing. Okay, so this thing is pointed by maybe we can actually use that, can we? Maybe we can use a reference counter. This is actually rather interesting. So yeah, we can try to use a reference counter. Another interesting approach, like instead of reference counting, would be to do a simple mark and sweep garbage collector as well. I'm not sure if reference counter is going to actually work properly. We'll see. But then the second option is going to be basically mark and sweep, because we know where the stacks start, right? So we can take these roots and we can BFS this entire thing, marking what's reachable, and then since we have an array of all of the nodes, we can quite easily see what's unreachable and just deallocate it like that. So this could be another way of doing this kind of stuff. But if we implement this simple mark and sweep, that means we'll need to decide at which point to call that mark and sweep. This could be interesting actually. So we could call it when there's no more nodes, right? So it's actually rather interesting. So if you're trying to allocate a new node, you see there's no more nodes, right? You can try to do mark and sweep and just like deallocate some memory, but if you can find anything, it's basically overflow. Okay. So, and the question is which one is going to be easier to implement. We can actually explore different approaches in here, right? So we can try to implement reference counter and then maybe mark and sweep if we have enough time, right? Is everything clear so far what we're trying to achieve? Is everything clear? The cool thing about this approach is that it doesn't require like garbage collection or anything like that, because effectively we're implementing our own allocator and our own garbage collector. But since we're implementing a very specialized garbage collector and very specialized allocator, it is actually easier than implement like a general purpose Malloc and free and general purpose garbage collector that has to work across several threads and stuff like that, right? We're not trying to implement our own garbage collector that is like in Python Python or like in Go, because these garbage collectors are very, very, very generic. They have to work for all of the possible sizes of the objects, all of the possible use cases. They're very sophisticated. A lot of computer scientists like defended like a lot of PhD theses on that and stuff like that. We're not doing that. We're implementing like a very like a garbage collector for a very, very small specific case, which is hundreds times easier. Hundreds times easier. So, and this is kind of like kind of reminds me about the situation with like game engines, right? So I used to implement like games on this channel. I'm gonna do game development at some point again. So, and people were constantly asking me like, why do you implement your own engine? Drake Soren, thank you so much for 11 months of Twitch Prime subscription.
Long time no see, Paging.
Thank you. So people were asking, why do you implement an engine? And this is because when people hear a game engine, they instantly in their head imagine something like Unity or Unreal Engine and something like that. But the reality is I was not trying to implement Unity or Unreal Engine because they are very generic, very big engines. What I was trying to implement is a very small engine in which I can implement my very small game, right? To implement a very simple small game, you don't need whole Unreal, you don't need whole Unity, you like actually need like a small, very small fraction of the functionality of these engines, and implementing that fraction is way easier than implementing the like Unreal Engine or Unity or whatever. Godot, how many engines we have these days, I don't know, I never used any of them. So, and this is kind of a similar situation, right? So, why would you implement your own garbage collector? Well, I'm not trying to implement a garbage collector like in Java or like in Python or like in Go. Like, I'm not doing that. I'm implementing garbage collector that works in very, very specific narrow situation. Very, very specific narrow situation, which is 100 times easier than implementing something like in Java. Right, here we have to just like, you know, garbage collect like fixed size nodes for a very specific data structure. You see what I'm talking about? It's kind of like similar. This entire idea of like implementing like small portion of functionality that does your job, like works not only in game development, it like works across the like software development generally. Okay, so I'm not really sure. It looks like we can use countref because countref will probably make it super easy. But I also kind of want to have an excuse to implement mark and sweep garbage collector, so we'll see. Anyway, let's actually start prototyping this entire thing. I decided to try to prototype this thing in Rust. Because why not? Because prototyping this kind of stuff in Porth is kind of difficult because Porth is really low level language and it's kind of difficult to follow right now because it doesn't have like a lot of good semantical and syntactical sugar and stuff like that. So I decided let's just prototype this idea in Rust, see how it works in Rust, and then I'm gonna just port this entire thing to Porth, right? And then re-implement the type checking of Porth in Porth. Anyway, hope everything is clear. I'm not going to close this thing yet. And let's go ahead and implement this entire thing. Porth. So how should I call this thing? Persistent stack, right? So here's the folder and I'm going to do main.rs. More like my ass. Haha, got him. Anyway, so let's write a simple hello world, right? So here's hello world because I haven't programmed in Rust for quite some time, so I don't remember a lot of things. So let me see if I still remember how to write a simple hello world. If I remember correctly, you have to do Rust C, right? So it will take some time. You need to recompile everything. Okay, and it compiled. And then if we take a look at what we've got a single executable, 3.3 megabytes executable. So what's the size of the entire Porth compiler? Okay, so the size of the entire Porth compiler is actually 428 kilobytes, but the size of a single hello world is 3.3 megabytes. So, yeah. I mean, it probably has like debug information or something like that. Anyway, so here's hello world. So I wonder how big is it going to be if we like strip it? Is it going to be smaller? Oh, it's actually smaller. It's actually smaller than the entire Porth. How about that? Anyway, so it was primarily some debug information. Okay, cool. So we need to implement the type stack, right? We need to implement the type stack. And to implement the type stack, we need the data type, right? So let's actually introduce it. So I think I'm gonna, since Porth has like 3 types, right? It has integers, pointers, and booleans. Let's actually encode them as enumeration, right? So we're going to say data type, and the first data type is going to be an integer. So here's an integer. Then we're going to have a pointer, and then we're going to have a boolean, right? So this is primarily for the demo purposes, right? So it's not going to have any meaning. It's just something that we want to put into the stack, right? So, and on top of that, we probably want to actually derive something like debug, so we can, you know, read that and so on and so forth. So maybe this entire thing is going to be clonable and copyable, right? Int 82. Thank you so much for 2 months of tier 1 subscription. Thank you, thank you, thank you. And welcome to our epic Rust Club. Finally, we're doing Rust. We've been talking for like half of an hour about Porth and stuff like that, but finally we're programming in Rust. Anyway, so let's actually implement like a single node that is going to hold our data type, right? So let me think. So it's going to be basically a structure, and I want to call it a frame, right? Because since we're doing a stack, the elements of the stack are usually called frames, I think, right? Usually, right? I don't know. Maybe it's specifically for call stacks. Right, so this is going to be a frame, and we're going to have something like type. Type is already taken, so let's call it data type, right? And this is going to be just a data type, and we need to keep track of the previous frame, right? We need to keep track of the previous frame. So I'm going to do previous, which is going to be basically a box to a frame, but I suppose it has to be optional, right? So something like this. But here's an interesting thing. Since I want to pre-allocate a lot of frames, right? I want to pre-allocate a lot of frames. Maybe it would be easier to actually refer to those frames as via the indices in the pre-allocated array, if you know what I'm talking about, right? So essentially, we can have something like struct FrameAlloc, right? FrameAllocator. Let's call it FrameAllocator, right? So basically, ator stands for allocator. The same way ctor in C++ stands for constructor. Dtor stands for destructor. In our case, ator is going to stand for allocator, right? So we're gonna call it FrameAllocator. Sounds good? Sounds good? Sounds Tamaguchi? Okay. So, and basically what we can have in here, we can have frames, right? So it's gonna be a vector of frames. And frames essentially are going to refer to a specific index within that array of frames, right? It's gonna be something like usize. And by doing that, by the way, we will make the borrow checker shut up, right? So essentially, here is the trick. If you don't want to deal with the borrow checker and all of this nasty stuff, lifetimes and whatnot, just switch from pointers and reference and stuff like that to indices within array, and that way you disable borrow checker. This is like a small trick for all of you Rust developers out there who got tired of borrow checker. This is how you do that. And so yeah. So not everybody knows that, but in Rust, there is a way to disable borrow checker without unsafe block. You don't even need unsafe block. You just like use indices instead of pointers, and there you go, you have no borrow checker. Indices instead of pointers is actually more common pattern for more complex data structure. Of course, because for more complex data structures, you need to disable borrow checker. Of course, it is a common pattern for that. So obviously, if you're doing anything complicated, you want to make the borrow checker to shut the fuck up. So that's why you're going to start using indices. Anyway, so here are the frames, and So we also need to keep a list of the free frames, right? So let's actually do something like this: free vector use size. Okay. So I have a couple of interesting ideas. So let me see. Let's make an implementation for FrameAllocator. It's a little bit cold in here, to be fair. It's a little bit cold in here. Maybe I should put on my my sweater. Anyway, okay. So what do we need in here? We need to be able to allocate a frame, right? So let's implement some stuff in here. I'm going to derive the default for this one and also the default for this one. And we need two operations. We need to, an operation that allocates a frame, right? So this thing will take a mutable self and will return the, actually it will return use size. And then we need a way to free a specific node. So it's going to take a mutable self and then let's call it an index, right? Use size and stuff like that. So I'm going to mark this as to do. Here's a very annoying thing. It's unclear, like use size, it is unclear that by use size we mean an index within this allocator. So I think it would be nice to have a type alias called something like frame index, right? So it's going to be frame index, it's going to be basically use size. I don't remember if you have to put semicolon here, maybe you have to. So, and now instead of use size, if we mean like an index, we're going to actually use a frame index in here, frame index. So, alrighty, cool. Another interesting thing I want to have in here, I want to be able to dereference the index, if you know what I'm talking about. Right, so you have an index and you want to take the reference to the frame by that index. So let's actually implement something like deref, right, deref. Is deref like a special method in one of the traits? It feels like it is, but I'm not a Rust developer, so I'm going to stay ignorant and just like use this word. Right, so this thing, if deref is going to be actually immutable, so I think we're going to grab it as immutable. We're going to accept the index, and I want this thing to return immutable reference to the frame, right? So, and of course, we have to have a mutable variant of this method as well. So we're going to have deref mute, and this thing is going to just return a mutable reference of this thing. I think this is all of the operations that we want to have for this specific allocator, right? Let's go ahead and implement them all. So first I want to check if this thing even compiles. So it's going to be rust c main rs. So data type, there is no default for the data type, which is rather interesting. So maybe we don't wanna... It's interesting. So I think we don't need that. Okay, so everything's fine. Everything's fine. We have a bunch of warnings, but they don't matter. They don't matter at all. Okay, so when we are allocating a thing, first thing I want to do. So imagine that you have frames, right? So you have a bunch of frames in here. So frames is equal to like something, A, B, C, and D. So what's interesting is that if you take a length of the frames, right? If you do length, it will point to the element after the last one, right? So length is equal 4. The elements are numbered from 0, 0, 1, 2, 3, and 4 is pointing here. So that means this is basically what you need to return to the user who calls alloc, right? So we're gonna do something like result, right? Here is the result. And then we need to basically push a new frame, which essentially means that we need to have maybe a default implementation for the frame, or maybe we're gonna accept initial value through that method, which we're gonna move inside in here. So we're gonna actually accept it by value, which essentially moves, if I remember correctly, Rust moves the elements by default into this thing, and we're gonna just move it into the vector, right? And after that, we're gonna just return the result. There we go. So we implemented a simple allocator, but it doesn't take into account the free, right? So we're gonna implement that a little bit later. Or maybe we're going to implement that way later when we actually try to implement the, memory reusage strategies. Maybe for now, I'm going to just leave it as it is. We won't be able to free anything. And I'm going to go ahead and try to derive this thing, right? So what we're going to do in here, we're going to take the frames, right? And I'm going to try to get, though we can actually try to be a little bit more safe in that regard, right? Because if I remember correctly, Rest App Docs API. So let's take a look at the vector. Where is the vector? So here is get. Could have actually searched specifically for vector get, right? Can I do something like that in here? It does not return me. It's very, very weird because. Is that because vector doesn't have get, or is that because this website is just like not working correctly? Because I remember vector had get. Or am I... No, it doesn't have get. Huh. It's very strange. Okay. Does it have get or not? I don't remember. Get. There is get. Okay, there is get. Okay, all right. That makes sense. Anyway, so essentially the reference is going to mean that we just do get, right? So we just get by that index. And index could be incorrect, by the way. And we're also going to do a similar thing for a mutable one, right? I'm going to do a similar thing for a mutable one. So if I try to build this entire thing, so it fails because this thing is supposed to return option, right? So is it going to compile now? What do we have in here? Consider change this to mutable. Yeah, this one has to be a mutable, oh sure. And there we go, so everything seems to be working. Okay, so we have frames, we have data types, we have allocators and stuff like that. I think the time has come to implement a stack on top of that allocator. Right. The time has come to implement a stack on top of that allocator. So let's actually create a structure. And so how are we going to call that? I'm going to call it type stack, right? So this is going to be type stack. And that type stack is going to have just a pointer to the top, right? So this is going to be just that. Option frame index. There we go. So this is basically what we have in here. Type stack. And in here, what we're going to have an operation that pushes a specific data type, right? So we're going to have data type. Of course, we're going to take a mutable self. Then we're going to take data type. And another important thing is we're also going to take an allocator, right? We're going to take an allocator. Maybe I'm going to take it as the second parameter in here, because this operation will allocate a node and it will allocate it into this allocator, right? So we're going to take it as mutable one. So this is going to be called FrameAllocator, and there we go. So this is what we need in here. And when we pop something, since popping does not really free anything because we're not implementing any memory preserving strategy, we're not going to take an allocator, right? So if we're going to do pop, we're going to just pop that thing. There we go. Cool. So let's actually, create the allocator somewhere. So this is going to be mutable allocator. And we're going to do FrameAllocator default. All right, so we're going to create a default frame allocator. Then we're going to create the stack, type stack default. And we're going to try to push a bunch of things onto that stack. Right, so I'm going to do stack push. So we're going to do a mutable allocator, data type pointer, then integer, and then the boolean. And then I want to be able to basically dump the content of that stack just to see if it even works or not. So we're going to do something like stack dump, right, and it will just dump it to the standard output. So we'll have to implement this entire thing. Is everything clear so far what we're trying to do in here, right? So we implemented like a simple frame, we implemented allocator that pre-allocated a bunch of frames, and now we're implementing stack that allocates all of its nodes into that allocator, right? So we're not doing anything special so far, right? So we're only preparing, so it's just like a setup, and the punchline is going to be a little bit later. Hopefully, if there will be one. I'm not even sure if there will be proper punchline. We're just exploring things. Okay, so we're gonna take a mutable self, yeah, immutable one. So let's see if this thing even compiles still. So we don't have a default thing, so let's create it like that. Derive default. Let me see. Okay, so everything seems to be fine. And if I try to just call this entire thing, it should fail with not implemented, right? So it panicked at 48 and it couldn't push anything in here. Okay, cool. So what we want to do, we want to create a frame, right? So in allocator, FrameAlloc. So we have to provide the frame. So, and inside of the frame, right, inside of the frame, we have to provide the data type. So I can just do data type. Right, so they have the same name, so I can just use it like that. And now I can do a very interesting thing. I can set the previous to the top of the stack. So I can just do SelfTop. And so this is the previous, right, there we go. So, and previous, if I remember, is optional. Yeah, it is optional. So, and then I'm basically allocating this frame and I'm moving it inside of the allocator, and this thing returns me a new index that I want to assign to the top. I wonder if the borrow checker is going to be okay with that. So, and also this thing has to be wrapped in sum. And I think this is basically the entire push. I think. Am I missing anything? I don't think I'm missing anything, right? So the only problem is that this kind of stuff could be, you know, like maybe borrow checker is not going to be okay with that. We'll see. We'll see. Why are you not trusted, Alif? I'm really sorry. So let me actually quickly trust you. So the bot is not going to ban you anymore. Really sorry. SelfTop needs some. Well, we'll see. The compiler will tell us. Okay. Wasn't even link. Well, SelfTop was a link. So, is there even a top domain? Right. There should be like a pair of domain, top and bottom domain. Right. All right. So there we go. So it's not really compiling. So it's 56. Okay. So that actually worked. Cool. The borrow checker has improved over the years, so we can even now write one-liners like that. I don't know why I feel like the borrow checker would be not okay with that, but it's totally fine. Okay, so now if we want to dump something, how are we going to dump that? We can just basically iterate through this thing, right? So we can do something like mutable top, and then I can just copy the top and basically while let some index equal top, we're going to, oh shit, we need an allocator to dereference the index. That's very interesting actually, right? So you have an index, but you can't access the frame without the allocator. So we'll have to actually grab this thing like so. Ater, actually we don't need the ater to be mutable, so we're gonna grab it as a mutable one. Right, then I do deref, right, I deref the index, and that gives me the frame, which I can now print. So let me quickly try to do that. So this is going to be something like this, right? So I dereference this thing, and I just grab the data type within that stuff. So it will just, you know, dump all of the elements of that stack, and then here, top is going to be equal to, you know what, I think we need to save that pointer, right? So this is going to be frame, right? Then I use the frame like this, and then the top frame previous. So it's gonna print that in like a reversed order, but that's fine, I guess, because it's like a debug information anyway. Right, so let's actually try to compile this entire thing, and something didn't really work well because this thing has to be debug, right? It has to be debug output. Are you gonna be fine now? Let me see. So data type, no field, oh, this one is optional one. Okay, so we know for a fact that index is a valid index, right? So, and if it's invalid index, that means we made a mistake somewhere. So we're gonna unwrap it in here. So, by the way, this is an equivalent of the of segfault, right? If you have an invalid index and you try to put an invalid index in here and you unwrap like that, this is essentially trying to touch the memory that you're not supposed to touch. This is literally a segfault, right? We disabled the borrow checker to the point that we can now have segfaults or something that's, you know, simulates segfault, like imitates the segfaults. You know what I'm talking about? Isn't that interesting, actually? When you start using indices instead of pointers, you're actually getting back to all of these problems that borrow checker is supposed to solve. So you have to be constantly aware of that while you programming in Rust, right? So you have a way to disabling borrow checker, but once you do disable borrow checker, you have to be aware that you're bringing back all of these problems that borrow checker is solving, right? So, and this is basically where you can segfault if you have like incorrect index. So, anonymous user gifted a tier 1 sub to Olive is a word. Thank you so much, anonymous user, for a gifted sub, and Olive is a word. Welcome to our epic Rust Club. Cheers, by the way. Okay. So, let me see. So that's fine. Let's see if it's gonna work. Okay, so we have to supply the allocator. And it worked. Look, it printed boolean, integer, and pointer, and we pushed them in a different order, in a reversed order, right? Pointer, integer, and boolean. So the stack actually works. So then we can try to do some other things. So we can try to pop the stack, and as we pop it, I think we don't really need anything, right? So let's give it a try. Because popping the stack is essentially, well, shit. Yeah, we need to take the allocator, but we need to take the allocator as immutable one, right? Because we don't need to allocate anything within that allocator. So this is going to be FrameAllocator. There we go. And then what I have to do FrameAllocator deref. This one is interesting. So, right, if you try to pop the empty stack, right, so the empty stack will have nothing. Should we allow popping from the empty stack? Let's actually allow that. So if let some index equals SelfTop, right, we're going to dereference that index and we're going to unwrap it, right, and then I'm going to do SelfTop frame previous, right, there we go. So that's basically what we want to have in here. So then I'm popping this entire thing. Okay, so I have to provide the immutable data. Okay, it still doesn't work. Types differ in immutability. Are you sure about that? Because, yeah, I didn't think we need that. There we go. So as you can see, we pushed pointer, integer, and boolean, then we popped one element. Right now we have integer and pointer, and then I can do push, right? I can push this thing back. Let's actually push another pointer, right? So what we should see, we should be able to see pointer, integer, pointer without any boolean. And as you can see, everything works. But there is an interesting thing in here. This pop leaked a node, right? There's only 3 elements. There's only 3 elements on the stack, but we allocated basically there's 4 nodes taken. We can even see that. Okay. We can do something like allocated nodes, and we can just go into the allocator. It's actually frames. Frames and take the length of the frames, right? So this is basically what we can do. To print ln has to be a macro. There we go. So as you can see, there is 3 elements on the stack, but we allocated 4 frames. So some of them are, you know, actually wasted. So which is rather interesting. which is rather interesting. So the most important thing here is being able to copy this stack, right? We want to be able to clone this stack. And to be fair, I think we don't really need to do anything special to do that, right? So if we just enable clone and copy, just copying a single number is already copying the whole stack. So this is the beauty of this approach. You need to split the stack. You don't have to copy anything. You just have to copy a single number, and there you go. Now you have two stacks. Pretty cool. Azura Akumore, thank you so much for thank you so much for 2 months of Twitch Prime subscription. Thank you, and welcome to our epic Rust Club. Okay, so that's pretty pogue. So if we just allow leaking the memory, so it's already working. So you can actually split the stacks and, you know, do this stuff quite easily. So Thomas 1992, thank you so much for Twitch Prime subscription. Thank you, and welcome to epic Rust Club. Okay. So let's actually test how this thing is going to work. So here is the stack. So let's call it something like stack 1, right? So we allocated, we basically pushed a bunch of stuff onto the stack, right? Then I want to create a copy of that stack. So I'm going to do stack 1, stack 2, and I'm going to assign stack 1 to that, basically copying it. Hopefully. Am I copying it? I think I have to explicitly say clone. Well, I mean, I don't have to explicitly say clone because I said copy, but let's actually remove copy. So we have to explicitly do the clone so we can see that we actually cloned the stack. Okay, so we created the stack, we cloned it, and now we can try to modify the stack 1, right? So stack 1, I'm going to pop the elements from the stack, so it's going to be 8, and then I'm going to push 8 data type pointer, right? So, and what I want to do in here is I want to print both of the stacks and just see that the copied stack still retains its original structure, right? I want to just confirm that copying the stacks actually works, and no matter what you do with other stack, with other copy of the stack, the copy of the other copy of the stack is actually stays retained, right? If you know what I'm talking about. Okay, so let me see. So we want to print something like println stack 1, right? So here is a stack 1, and then we want to do this thing, and this is going to be stack 2. So let me see. All right, so maybe I should have actually put a little bit more spaces in here, right? So we're gonna just do something like println just to add more spaces. Is it gonna be sufficient? Yeah, it is, seems to be sufficient. Okay, stack 1, as you can see, it contains pointer, integer, pointer, because we pushed pointer, integer, boolean. Then after cloning it, we popped the boolean and we pushed the pointer. So that's why on stack 1 you have pointer, integer, pointer. But stack 2 still retained its original structure, boolean, integer, pointer, the one that we had before cloning it. Right, so yeah, the one that we had before cloning it, so it still retained it, even though we popped the stuff and, you know, the other stuff. And it's still allocated 4 frames, so essentially instead of like linked list, in reality we have a tree, right? So it kind of resembles the Git history, if you think about it. Yeah, it actually kind of does. This is basically a Git history. Right, we can even try to maybe dump the structure of the... Let's actually dump a graph with shit. How about that? Because we can do that, right? Allocator has an access to all of the frames, right? So, and in the frames we have the pointers to the previous one, so we can quite easily dump the graph with data and just look at this entire thing. So let me quickly do that. FrameAllocator, we're gonna do dump dot, right? So we're gonna take it as immutable. It's actually pretty cool. I love how every stream turns into graph stream. Only the ones where we have to work with the tree data structures, right? Because every time you work with the tree data structure, you want to kind of visualize the tree, and the easiest way to do that is graphics. So why not? All right, so let's do print ln, and this is going to be dgraph, and we're going to call it frame, I don't know, stacks, something like that, right? So this is going to be stacks. Print ln, and we're going to just do something like this. So in here, by the way, visualizing this entire thing is going to be super easy because we don't even need any recursive algorithms. So we can just iterate through all of the frames, right, and just dump them as edges. So that should be sufficient, I think. I think that should be sufficient. So let me do it like so. Frame in self frames, right? There you go. Here we have a frame. And let's do it like this. Print ln 1, 2, 3, 4. It's going to be node and then ID of the node, and then we can have a label like so. This has to be like a debug one. And then I can say, okay, I probably need to enumerate this entire thing, right? So I want to enumerate it, so I have an index and the frame, right? So this is what I want to have in here. So here's the index, and then for the frame, I have to take its data type, and that should be sufficient enough. And the second thing I want to do in here, well, it only makes sense if you have the previous one, right? So we have to do something like if let sum prev index equal frame previous. We need to basically connect together these two nodes. Node that to node that. So the first one is going to be just the index, and this one is going to be the previous index. And it only makes sense if you do have that previous. Right, that's why we have a condition here. And that should be enough. So let's actually try to compile this entire thing. So you have to do it like that. Thank you, compiler. Very cool. Oh, do I have to like escape this entire thing? I don't really know how do you type it. Do I have to do double of this thing? I think you have to do double. I actually like guessed it, I think. Enumerate exists only for word, but its trait is not satisfied. So do you want me to do iter? Do you want me to do iter or something? Yeah, it wanted me to do iter. Okay, cool. So let me see. Now instead of doing that, we can do something like iter dump dot, right? So let's just dump the dot. And here is the basically graph with data structure of these nodes. It would be nice to actually save that to some sort of a file, right? So to save it to some sort of a file, I think dump dot should accept, you know, the sync into which you want to save all of that, right? So, and sync is basically going to be anything that implements, you know, writable interface, right? So we want to have something like this. If I remember correctly, to write into this writable interface, you have to do something like write-ln, right? And then you just use sync. And I feel like we have to get it by a mutable reference, right? So I don't quite remember how to do that. So the compiler will tell me, hopefully. Hopefully the compiler will tell me. But anyway. Write is not found. Okay, so let's actually try to see where write is located. Where write is located. So it's located in somewhere in IOR, right? So we have to do something like use std IO write. Okay. So, okay, this entire thing. Expected nothing, expected results. So we have to, what would be easier? I think the easiest thing to do in here would be to like dump dot to return IO result nothing, right? Like this. And for each individual write, we could like put a question mark in here. So in case of like error, it will just fail, and then at the end in here we can just do OK. Is that how we do that in Rust? I think this is how we do that in Rust, right? The usual thing. So, and let's use std.io. Right. So, and in here, I guess at the end in here, we want to like unwrap this entire thing, but it complains about not being able to find the, you know, instance of writable interface. So we'll have to open the file. So if I remember correctly, you have to like use file and you can basically create it, right? You can do file create in here. Yeah, there we go. So this is what we can do. So let me try to do that. I'm going to do use stdfs file, right? And I can just like, you know, file create output dot, right? Output dot. It didn't really, well, we have to unwrap it, I suppose, right? So, well, so create should return option, right? Oh, a result, rather. Should return a result. And we accept by immutable, so we can just do unwrap and then just do something like this. This should work, right? So it seems to be working. Okay, so and now if you take a look at output dot, there we go, here is our output dot. Isn't that cool? I think that's pretty cool. So now what we can do, we can just do .tsvg o output dot. And it generated an SVG file, which we can finally open in Chromium. And there we go. So here are the two stacks. The first stack has pointer integer pointer, and the second stack has Boolean integer pointer. Right, so we have two stacks and they share two elements. They share two elements, and we derive that information from the allocator, right? We derive that the information from the allocator. That's actually pretty cool. So we have a very simple debug tool. Cool. But again, I want to do the same thing as I did for the tree stream. I want the program itself to actually, you know, call GraphViz and stuff like that. But luckily in Rust it's a little bit easier. Right, in Rust it's a little bit easier to do because it has like command interface or something like that. I don't quite remember. Anyway, so let's actually do it like this. Let output file path. I'm gonna save this thing output file path, put it in here, and we want to do a logging. We're gonna say info generating this thing output file path, right? File path. There we go. So then we generated this entire thing. Then I want to call an external command, but I don't quite remember how to do that. So command, I do remember there was a command. There we go. So there's a process command, and that's pretty straightforward. Not gonna lie. So you just create the command, you provide the arguments, and you take the output, and then you expect that it didn't fail. So okay, so let's actually use that. Can your C do that, by the way? No, it cannot do that. Process command. In your stupid C, you have to do fork, exec, and stuff like that. You have to first fork a child, then you have to execute the child, you know, the usual stuff. Anyway, so sorry. New dot, and then we have to provide the arguments. So this is going to be args, and what going to be the arguments? The first argument is going to be tsvg, then o, and then we have to use output file path, right? And then we have to call the output. And do we have to do the output? Because I don't really care about the output, right? But it feels like that you have to. So fn output. So executes the command as a child process waiting for the finished. Well, you have to do that apparently. Okay, so but maybe I can just throw it away. So it's going to be args, then the output, then expect expect dot command should have executed successfully, but it didn't, right? Okay, so if I try to now run this entire thing, it didn't freaking work because this thing is not a macro yet again. Okay, so what do we have in here? Consider using, okay, so we have to put a semicolon in here, and cool, it generated this thing, but it didn't log the command that it was executing. Is there any way for the command to actually log what it's executing? Because it's not particularly convenient. I think, so there's a status. I didn't think so. Is there something like echo? Status. So you can use status instead of output. Is it gonna echo the command? Is it gonna echo? Executes a command, the child process waiting for the finish. By default, it doesn't echo. So I need like echo the command because I want to see what's currently the command executing. Okay, whatever. So let's continue. Let's continue. What's gonna be the next thing? The next thing that we wanted to explore is basically some sort of a reference counting, right? Some sort of a reference counting. But for a reference counting, we need to be able to free the nodes, right? We need to be able to free the nodes. I think the easiest way to free a node is just straight up add that node to, to the list of free ones, right? There we go. So, right, so we're trying to free a specific index and it goes into the list in here. And when we're trying to allocate a new node, instead of grabbing it from the vector, first we have to check whether we have anything in the free, right? So this is what we can do in here. So if self-free_len is greater than 0, we have to basically reuse a single node from here. Otherwise, we have to like allocate a new one. Oh, and here is an interesting thing. Here is an interesting thing. You get back to all of these problems that borrow checker is supposed to solve. What if you double free a node accidentally? You're gonna add this node twice to the list, so the next alloc is gonna reuse already allocated node. So you'll have to add some sort of a check that checks that you're not trying to free already freed node, or that the node that you're trying to free is even correct. So you're getting back to all of these problems. This is actually pretty amazing, I think. You're starting to have sec faults, you're starting to have like double freeze and stuff like that. You should use static size arrays. Vec is kinda cheating. I feel like you don't fully understand the meaning of word cheating. Cheating is going against the rules, right? At least this is the definition I know. There's no rules. What rules are you talking about? So... oh my god. Anyway. Imagine like accusing me of cheating in an environment where there is no rules. Like you, by definition, in that environment, you can't cheat. Like it's just like you made up in your head your own rules, and you're accusing me of breaking rules that you made up in your head. Well, cool. So I'm happy for you. Anyway, so I think I want to make a small break because I need to make a cup of tea. And after the break, we're gonna implement the allocation from a list of free nodes. Anyway, okay, so let's continue. So how we're gonna actually get the free node? I think we have to do a pop. If I remember correctly, in Vec there is a very convenient method called a pop. Let me see. So where is the... Here is the, and what's interesting about is that it returns an option, right? Which means that if this thing is empty, it will return nothing. So we don't really have to check the length. What we can do is just like instead of length, we can do, and here we can have some index, rather some result, right? which we can just reuse in here. So here is some result, and essentially I need to do self frames result, and I need to move the initialized thingy in here, right? So this is going to be init, and then I just return the result. How about that? How about that? How about that? Looks cool. Yeah, so that's basically what we're doing here, I think. So here's the result, and then init result, blah, 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 blah. I'm just thinking, like, my brain sees a result in both of the branches, and I keep thinking, can I compress that? If you know what I'm talking about. And it feels like I can't really compress that, and maybe I shouldn't bother trying to compress that, so maybe that's fine. That looks fine, because the most logical thing in here is just like move it away like this, but you can't do that because the result in one branch and result in another one are two different things. Right. Yeah, it's kind of difficult to compress this code. I don't see a good way to do that, and anyway it's going to be just like meh. Okay, go. So we implemented free, and every time we pop something, we can now free things. How can we test this entire stuff? Let's go ahead and just remove the stack 2, and let's just work with the stack 1, right? So we're gonna only have stack 1. And every time I pop something from the stack, right, so we are essentially dereferencing this thing, right, I can try to do iter free, and I'm freeing the index, right, I'm freeing the index. So after that, I can do stack 1 pop, and I can pop it 3 times, and what I want to see at the end of the day is how many nodes we have allocated. These frames, and I can do iter frames. Oh, this one is actually kind of difficult to tell because we're reusing the frames. So the length of the frames is going to be equal to 3 no matter what, right? Right, allocated these frames. Okay, let me see what's going on. So here's the pop. So we've got some sort of a donation. Holy shit, that's a pretty big donation.
Thanks for the streaming. I always learn something.
Just a second, I need for my Streamlabs too. Thank you, Anonymous, for $50 donations. Are you Mr. Beast? You're donating so much money. Thank you so much. Thank you for the streaming. I always learn something. You're welcome. You're welcome. Thank you for the support. I really appreciate the support. Thank you, Mr. Beast. Cheers. All right. So thank you so much. Really, really appreciate it. You didn't have to. I didn't think I deserved this much, to be fair. Right. I'm just like shitposting on the internet. Come on.
Not as much as the previous guy, but thanks for the content from Maswell.
Thank you so much, Ben Dershall, for 14 months of tier 1 subscription. Thank you. Really appreciate it. If let is basically a match statement with just one pattern match, yeah. And this is something that kind of annoys me, to be fair, because it makes it difficult syntactically to evolve into a match statement. You see, quite often you start with if let because you want to handle only one case. But then you want to start handling more cases, and that means you have to rewrite the entire structure to just migrate to match. It would be kind of cool if this if-let construction was designed so it's super easy to turn it into match, because that's quite often what you want to do. You know what I'm talking about? There's just like something really, like there's some friction between if-let and match that always annoyed me for some reason. Sorry for being rude in a PR before. I tried to refactor your code once again using generators, but eventually I got into heterogeneous data structures, which I could not implement using Rust type system. Don't worry about being rude in pull requests. at all. This is totally fine. I do not read pull requests, so I didn't even see that. I have no idea what you're talking about, so don't even worry about that. So, yeah, don't worry about that. That's totally fine. So let's continue. So I want to do a pop. I just want to see, yeah, I want to see that we allocated like 3 frames. Right. So this is what I was talking about. Let me see. Pop. So we have to provide ATA. I think I can use a little bit of Emacs magic. Right. Okay. So here's the ATA free. Consider changing this mutable reference. Okay. Oh, yeah. You see, pop before never deallocated anything, so it never modified the state of the allocator. So now it frees things, and now it needs to modify the state of the allocator. So let's go ahead and do that. Okay. So we've got this thing, and this thing has to be immutable now. Man, I love busy work the Rust actually forces on me. I really love that. Okay, like, you know, you program in Rust and it forces you to constantly change like mutable reference to immutable ones, like change that and that and that, and it feels so productive. It feels like you're doing a lot of things. You know what I'm talking about? Okay, cannot borrow as mutable because it's also borrowed. Oh, I see what you're talking about. I do in fact see what you're talking about. The person of fun subscribed with Twitch Prime. Thank you so much, the person of fun, for subscribing with Twitch Prime. Welcome to our Epic Rust Club. So essentially, the only reason we need this frame is because we want to get it like the previous value. So what we can do here is we can grab this thing and just literally inline it like so and put it here. That way we briefly basically borrowing the ATA and then we release it so we can borrow it again. Anyway, thank you Einstein for 4 months of Twitch Prime subscription. Thank you, and welcome to Epic Rust Club. So that way the borrow checker is not gonna complain. We have so many subs today. Holy shit, thank you Jay Riesel for Twitch Prime subscription. Thank you. Welcome to our Epic Rust Club. Rust compiler is so helpful, to be honest. Such pretty error message. Speaking of pretty error messages, like Vim compilation mode or whatever the fuck it's called, you know, the thing that handles the make command, it has a hard time parsing this thing without custom regular expressions. Vimmers, do you know what I'm talking about? I think majority of the Vimmers just use the like a specialized plugin or extension for Rust, which kind of handles that. But by default, Vim has a hard time actually processing this thing, and it's kind of funny. I can actually show you. Because I was planning to use Vim for today's stream, and then I encountered that problem, and then I thought like, I don't want to deal with that. So let me see. So persistent data stack, right? So if you go to here, and if you try to, first you have to say to make PRG program, right? So let's set it to rustc main.rs, right? And if you do make, right, so here's an interesting thing. It calls the compiler, and then it will parse the first error, right? It will parse the first error, and then it will jump to that error. But here's an interesting thing. It will parse this as a file name to which it has to jump, right? So, and if you press enter, your entire screen is going to be empty, and you're going to be wondering why until you try to save your file, and it will say it saved it to --greater space main.rs. Right. So then you can quit Vim, and you will find that you have this file. Which you can't even like delete properly, right? Because it looks like it's a flag to rm, so to delete it you have to put like /. Well, I googled a little bit like around the internet, so the usual solutions are to mess with error format, right? In Vim there's a thing called error, I think it's error fmt, help Error format. Yeah, it's an error format. So basically it's a list of regular expressions that are responsible for parsing this thing. And the other solution is to use specialized extensions for Rust, which parse these kind of things themselves, and they don't have that problem. So since every Vimmer uses these specialized extensions, I'm the only one who's encountered that problem. So I just thought that I don't want to deal with that. So yeah, there we go. Just wanted to share that information with you. Emacs has no problems parsing all of that, so it's just like, it's just that. It's kind of funny. Choose, by the way. Can your Emacs do that, by the way? Can your Emacs do that? I don't think so. You know about error format? I think it's like an archaic thing that nobody uses. Almost like the make command. The Kate has the same problem with those errors. Well, the problem with the error format is that it's very annoying to modify. So if you want to fix that problem, you have to go through a lot of pain to put regular expressions in an error format in a particular order. So it's kind of like something that you don't want to mess with. Anyways, so I think we should fix the problem now. There we go. So the problem has been fixed. And now as you pop things around, it will deallocate this thing. But it still says that it has allocated 3 frames. You see? It still says that it has allocated 3 frames. And this is because the deallocated frames are located in the free list, right? So, and if we do something like println, right? If we do something like println, freed this amount of frames. So it's going to be iter free len. So it will say how many frames it's allocated and then freed 3 frames. So yeah. And if you try to allocate some stuff afterwards, right? If you try to maybe push integer 1 time, you're gonna have still allocated 3 frames, but freed 2 frames because 1 is already taken, right? So that's actually pretty interesting. So we have a thing that can free the frames now. The next thing is to free the frames automatically, right? So one of the solutions that we want you to explore is reference counting, right? We want you to explore the reference counting, and where we're gonna do a reference counting. The most logical thing to do the reference counting is in the frame itself, right? So let's actually put like some sort of a field in here, ref count, which is gonna be usize. Is that a good idea to do it like that? I think so. I think so. And who's going to be responsible for the ref count? I think the allocator should not be responsible for the ref count. I think it should not be responsible for that. It should be responsible, the stack itself should be responsible for that, right? As you pop an element, right, you decrement the ref count for the new top. And then as, you know, the ref count reaches 0, right? You essentially delete this entire thing. All right, so that's pretty cool. So that also means that we cannot clone this stack like this anymore. You can't clone it anymore like that. So essentially what we have to do is to implement our own clone method that also increments the ref count for the current thing in here. Yes, that's what we need to do. So I'm going to remove the clone from here, right? So I'm removing the clone, and I'm going to implement my own clone in here. There we go. So, and this thing is going to take... Oh, this one is interesting, by the way. I do need my own clone, by the way, right? Because I will be dereferencing the pointer. And to dereference the pointer, I need allocator. So this is going to be like a special clone that on top of taking, I think it will take immutable self, it will also take a mutable allocator, FrameAllocator, like this. And it will return, I suppose, self. Slef. Right, it will return self. Cool. Alrighty, so here's the frame, so here's the data type, the previous one is going to be that, and what's interesting is when you create a new frame, right, so we're pushing a new frame onto the stack, ref count is going to be 1, because the only thing that is pointing at that frame is the type stack itself, right, so it's going to be just 1. When we're popping the thing, right, when we pop in the thing, I need to dereference this entire thing, take the previous, but on top of that, I also have to decrement the ref counter. Decrement the ref counter. So let me see how we're gonna do that. So here's the frame. I think it has to be mutable. I think I need a mutable frame, so this thing is going to be basically mutable. Then, within that thing, I'll have to take the ref count and decrement it, right? I'm decrementing this thing. And then, this one is going to be rather interesting, actually. So I assign frame to the previous one. And the only time I need to free it is when frame ref count becomes 0, right? It reaches the 0 and then I want to free it. But that creates a lot of like weird stuff because we borrow ater in here and we keep it borrowed up until in here, so we cannot borrow it for mutable again. So that means we have to do all of this stuff like in a very confined scope, right? We have to do that in a very confined scope, and the question is how can we even do all of that? So we can actually wrap this entire stuff in its own scope. So the ater is gonna stay borrowed only within that scope, right? And here we're going to move this condition at the end of that scope, right? We're moving it at the end of that scope, and we're gonna assign it to some sort of a variable, something like delete, right? And then if delete, you go and free it. So you see, we only keep ater borrowed here, and then we unborrow it, and then if we need to delete it, you borrow it back. So basically we're moving that condition from here to here. So, and borrow checker forces us to do that. So the only reason we do it like that is because borrow checker wants us to do things like that. It would be kind of cool if I could have a block as a condition like that. If you know what I'm talking about. Rust developers, do you know what I'm talking about? Right, so I could just have a block that is like an expression. Is that even possible? Can I just take this? Can you do? I have no idea, can I? So that's my question. That would be actually kind of cool. So basically I say, borrow it for the duration of calculating the condition, and then unborrow it, and then borrow it back to do this operation. So, okay, first of all, I want to check if this entire thing compiles, right? Because maybe I did a fucky wacky and oopsie doopsie. Okay, I didn't. So now, let's give it a try. Right, so I'm going to put it like that. This is the wackiest code I've ever written, and it fucking works. What the fuck? This shit will confuse anyone. So essentially you can have sequence of like statements that lead to a condition. This is so cool. You can do that. You can do that. So, and the reason why I even thought about that is because you can do this kind of stuff in Porth, right? In Porth, there is like a whole paradigm that I discovered, right? I discovered the whole paradigm in Porth, where like you have a while do, right? And you have a condition in here, condition. But since Porth is like, it doesn't have any blocks in here, you can actually use the space between while and do as the body of the condition. Right. So, and in fact, it's used quite often in parsing to break out earlier. And this is basically what gave me the idea of using like a block of code as the condition for if. So, and I'm surprised it works. So maybe I'm gonna do it like that. That's actually pretty interesting. Huh. It's really wacky. Do people even write Rust like that? Mm-hmm. Yeah, so this thing does in fact feel so ill. Like, somebody's gonna look at that code and they're gonna go like, what the fuck? Like, what the fuck does it even mean? Like, holy shit. Lots of people do. Okay, that's actually pretty cool. Because it's kind of convenient, to be fair. Right, it is kind of convenient. Okay, so we borrow this ater, we remove its reference, right? Then we set it to the previous, and if a reference actually reaches the 0, then we do free it. And it's kind of important because you cannot just move this thing in here, because you have to unborrow it first and then borrow it back. That's what you have to do. Okay, so on pushing we do reference count 1, here we decrement the reference, when we dump we don't have to do anything. On clone, this one is rather interesting, right, on clone. What we have to do is we have to take eta, first of all, if let some index SelfTop, there we go. And I do ater deref as mutable, right? So this is going to be index, and then I'm going to take a mutable frame. There we go. So, and when you clone it, you have to do ref count plus 1, right? So there is another count, another reference pointing at that specific thing. Okay, that's pretty cool. That makes a lot of sense, actually. It makes a lot of sense. And then I have to return self, which uses, well, it just clones itself, I suppose. SelfTop, SelfTop. I guess that's it, right? So we just check if top has anything, and we dereference that top, and we increment its ref counter, and we just like clone them ourselves. It might be awkward if you ever need to debug that if, but I find it easier to read that shunting that to function as people usually do. Do people even step debug Rust? Because like I tried to step debug Rust and the tooling for that was actually very horrible, so I'm not sure about that. So Root Black 45, thank you so much for tier 1 subscription, thank you, and welcome to our Epic Rust Club. So I think here I need to unwrap this entire thing and everything seems to work. I think we implemented like a reference counting, what the fuck? Did we? Did we implement a reference counting? I think we did. So how can we test all of that? How can we test? So we can actually log something when every time we free. Every time we free. So can the reference counter count itself? I don't understand the question. It is possible, but I think you need LLDB for some reason. I don't think I said it's impossible. I said that it's very annoying. And I said that I tried that and it was in fact very annoying. So in like quite often if you want to debug something with Rust, it's just like easier to do printf debugging. LLDB can get painful. Yeah. It's kind of interesting that modern environment kind of encourages you to do printf debugging, because step debugging can be pretty powerful. It can be pretty powerful and can help you to find very nasty bugs. You can blame nasty bugs for like weak type system or something like that, but at the end of the day, step debugging is actually very useful when you get used to it. So we probably want to, okay, I want to dump the current state and just see how useful that is. But on top of that, I want to be able to see what frames are freed. You see, like the current dump is not going to work, right? Because some of the frames that you're referring to, they could be freed, so they're not available anymore. But what's funny is that maybe it doesn't even matter, you know? Maybe it doesn't even matter because we can just mark those nodes in a very special way. Right. The question is, how can we mark them? So I can basically set up the connection between nodes in here. I set up the connections in here, and then after that, I can do the rest of the stuff. It would be easier if the free nodes were set, right? It would be super easy if they were set. In the final implementation, they don't have to be set. We just need to be, well, maybe it doesn't really matter, right? So we're not trying to be fast or anything. Does vector even support something like find? Can you find? Right, contains. Yeah, it does have contains. Okay, so I can just search for a specific element. Right. So, and essentially I can do, so frame, we found a frame, and we can do something like if self-free contains index and it does not contain, we basically not gonna even render this entire thing. So it is slow, it is linear search, but this is a debug output, right? So this is not going to be like a final production solution. And in the final production solution, we don't even need to do this operation. So this operation is only needed for debug purposes. So yeah, that's totally fine, I think. That is totally fine. So let me see. So can we have, on top of the label, I also want to have something like a counter, right? So I can do something like this. So this is going to be the string, and I think you have to use double quotes, right? So this is going to be double quotes, and here we can use the counter. So I can do frame ref count, right? Can I do that? So it didn't really work. So here is the index. So it has to be a reference for whatever reason. So we don't have a file, so let's actually make it a file. I like the simplicity of reference counting, actually. Is never used. Can I just allow that code? Because it could be dead sometimes, just like myself. Haha, self-deprecation. Is never used clone. I think we're gonna use that. So dump, what is dump? Dump is not probably needed. Whatever. Okay, so let me see. So we have stack 1, right? Then I want to do stack 2, and I'm gonna do it like this. I'm gonna clone using the allocator, right? So you can only clone it by using that allocator. Then we do stack 1 pop mutable eta. And then stack 1 push mutable eta data type pointer. Okay, so this information is useless. Anything else we need to have in here? Let's try to call this entire thing. And we have SVG generated, and let's take a look at this entire thing. Okay, cool. So this doesn't work. I think you're supposed to have 2 in here, Right, I think you're supposed to have 2. But something went wrong during the cloning process, and I wonder what exactly. So let's find out. Let's find out. I wonder what. So if I just don't do any of this stuff, will it work correctly? I think it does. Right, I think it does work correctly. Yeah, okay, this one is very interesting. This one is very interesting. So basically you have 2 pointers that point in here, right? So at this top, you pop one out, and this is the new top, right? This is the new top. And as you push, right, as you push, how is that? How is that different? So there's a bug in push. There's a bug in push. So it's almost like I have to take the top and increment it by 0. It's kind of unclear how. It's really unclear how we're supposed to even do that. Like, yeah. It's really unclear. So the easiest way to work out this kind of stuff would be Marcus 3, but maybe. Okay, so let's actually try to replicate the situation. So we have this one, right? Then this one and this one, right? Actually, at the beginning, right, you have 1 pointer, so here is 1. Then you push, and you think, right, and you point here. For a brief moment you have 2 of them, right, but then you go back to just 1, right? And because of that, it doesn't really make any sense to increment it twice or anything. Then you create another one, so a brief moment is going to be 1, but then you're going to move it out. So at the end, you're going to have this thing. So you clone the stack, right? You clone the stack, you have 2 in here, right? So by popping from the stack, you essentially decrement this thing. You decrement this thing, go back, but that effectively means that now there is 2 pointing in here. So pop, while decrementing one thing, should increment another one, right? Should increment another one, which does not make much sense to me. Oh, I see. So, and we have a situation with a single stack, right? You have a situation with a single stack, which looks like this, right? So there's a 1, 1, and here is the pointer. So by popping the element, you kind of move down here, right? You move down here, and that makes it 2. But then you sort of dereference this thing, which brings it back to 1. Right. So you have to kind of like, it's kind of finicky to keep track of all of this kind of stuff, right? And the question is it even worth it? But if we come up with like a proper rules to do all of that, maybe. It feels like this kind of stuff should be probably handled on a different level. Yeah. It feels like it should be handled on a different level. Maybe not. So essentially the allocator itself, when you free the node, it should look at the nodes it point to and decrement them as well. I think that's what has to happen. Right, so that's essentially what's going on. Right, because that's essentially the operation that we're trying to do in here. Or also, When you add a new node, right? When you add a new node, and that node's point to something, we'll have to increment it as well. It feels like it has to be interplay between the type stack and the allocator all the time, right? It's basically the interplay between them, and I'm not sure. It's kind of painful, to be fair. It is kind of painful, and I ran out of T. So mark and sweep would be actually super easy, to be fair. With the mark and sweep, you just have to keep track of the list of all of the stacks, and then you will just iterate through all of them, marking which ones are already visited, and then you remove everything else. So that will be actually way easier. You won't even have to think about like when to decrement or increment, or whether you forgot to do that or not, or something like that. So yeah, maybe we should try to implement mark and sweep. What do you guys think? We can try to do that, because I feel like it's easier for some reason, right, than messing with like ref counters and whatnot. So okay, for the so instead of ref counter, right, let's actually go ahead and remove the ref counter. So that way, so we don't have a ref counter, so we don't have to print it in here. Okay, so we don't need to do that stuff in here. We don't need to have that stuff, and we don't have to decrement anything. Oh, and yeah, by the way, so if we're gonna do mark and sweep, when we pop something, we don't even have to care about this kind of stuff. We can just go ahead and like deref it. So yeah, we can bring back. So we can do that. So it's gonna be top. Then yeah, we don't even have to do any of this stuff, don't we? So you pop, you just do that. Okay, so just let it leak. Just let it leak. Let it leak, let it leak, let it leak, oh, let it leak. Memory costs nothing, let it leak. Okay, so when I clone something, yeah, so that essentially means we can just use the default clone. Okay, and here's where we clone all of that. Okay, so let me see. Frame, previous data type and stuff like that. Let's have something like visited false, visited boolean, I mean, right? So visited boolean. Visited boolean. Is it gonna be on the frame, or is it gonna be like a different data structure? That's also a good question. It is also a good question. And what's interesting is that now, if we're gonna do it that way, I need an operation that like checks whether the frame is already freed or not. So that's kind of a problem in here, right? We want to be able to do that. But maybe we can have additional flag that indicates whether something is freed or not, right? So that way we can easily skip the freed frame, if you know what I'm talking about. That's actually an interesting idea, like free, right? By default it's going to be false, right? And that way you can quite easily check all of that. You know what, I think I want to make a small break because my brain is kind of like shutting down. So, and I'm already streaming for 2 hours, right? I'm already streaming for 2 hours, so definitely want to make a small break. So alright, so mark and sweep is actually like solves some problems, but it introduces another problem, is that now I'll have to have a fast operation to check whether the frame is free or not, and that will require me introduce like another field in here. So maybe I want to still stick with the reference counting idea, right? So both of the ideas like have their trade-offs and stuff like that. But if we can nail down the reference counting, I think it's going to be, you know, relatively convenient to work with. So maybe what I'm thinking is that for the reference counter, we should get rid of the free operation, right? So maybe instead of free operation, we have to introduce like something like acquire. Acquire? Is that how you spell that word? Did I spell it correctly? Acquire by, okay, so that's gonna be acquire. Right, self. I'm not sure if I'm moving in the right direction, by the way, so I'm just experimenting. Right, so this is gonna be a size. This is not implemented, and then we're gonna have something like a release. Right, so it's gonna be mutable self index use size, and this is going to be to do. So you can acquire something and you can release something, and we're not gonna have like a ref or anything like that. So an acquire will increment the reference counter, and release is going to decrement the reference counter. And if it reaches the like -1 or 0, or like, why did you say -1? If it reaches 0, we're going to basically free it ourselves. So when we allocate something, I think it will automatically acquire that thing, right? So it will acquire it. And we'll have to basically quite carefully call these two functions, right? I think that's what needs to happen. All right. So, and the question is, where should we store the reference counts? We can store them somewhere here, maybe, right? So maybe the frame itself should store them. So it doesn't really matter, right? So because this is a prototype code, we can just store it somewhere here. But it makes it rather inconvenient. Right? It makes it rather inconvenient. It's going to be ref count, because the reason why it's going to be inconvenient, by the way, is because you have to provide it in here in the initialization, right? You have to provide it in here initialization, but if we do it like this somewhere in a tuple, right, it's going to be a little bit more convenient. So what is more convenient? It's kind of difficult to tell, right? Because the user should just stick with this thing. So this one is definitely going to be convenient, but I don't remember how to access specific fields of the tuple. How do you work with tuples in Rust? So tuple, let me see. So here's the tuple, and if I want to access like a very specific field, it's a .0, .1 or something like that. Okay, so this is basically what I want you to see. Okay, so then I do frames result. So let's actually let the compiler do the job. Like so the compiler should just tell me what to do. Okay, so this is going to be the 0, and then here we're going to have frames. Might as well just do something like this. 1, because we acquire this thing right away. Right, and then here we push init and also 1. So, and when I get this entire thing, I also want to get this, right? I'll have to map it, by the way, right? So I'll have to do something like x, 0. And here also I'll have to do something like x, 0. Hopefully that will be sufficient enough. I'm not sure if it will be sufficient enough. Let's see. Expected, expected because of return speed, but got just frame, which is rather interesting. So that means I have to explicitly just do that stuff. Sure, that is totally fine. So, and in a frame, I got this thing. So this is not a frame anymore. It's more of like a frame and ref count, right? But I don't really care about the ref count, so I'm gonna just simply ignore that thing. Okay, does it work? It seems to be working. Okay, cool. All right, so let's actually implement acquire, right? So when you try to acquire something, we do frames index, and then I take 1 and I increment it by 1. There we go, so I just incremented it. Then if we release something, I'm going to do frames index 1 minus 1, and if it reaches 0, right, if self frames index 1 is less or equal than 0, I don't think it can be less than 0, so we're just going to do equal 0, we are going to free this thing, right? We're going to free this thing. So when we free the thing, this one is quite important. So we also have to release whatever it's pointing at, right? So this one is very interesting, right? We have to do self frame frames index self frames index 0. Then we'll have to take the previous, right, the previous, and if the previous has anything, right, if let sum pref index, right, if it does even exist, we'll have to release it again, right, so we have to release pref index like so. So it sort of forms the chain, right? So it will create a chain reaction. So I guess the need for this sort of chain reaction created the complication I was dealing with, right? So you need to like cascade this kind of like releases and stuff like that, right? So, and obviously the borrow checker is probably not going to accept that, right? So I'm just like outlining the idea, right? So let's see if it's gonna work. And it worked, surprisingly. Like, I'm surprised the borrow checker is fine with that. Oh, this is because I'm borrowing this thing and I'm releasing it right away, right? So that kind of makes sense, I suppose. Can I just like have something like, I don't even know. Well, I guess that's fine. It's kind of a weird code, but it's fine, I guess. I guess it's fine. So we have acquire and we have a release. Cool. So if I try to run this code now, it kind of works, by the way, it kind of works. Okay, in the stack, when I push something onto the stack, right, it right away acquires that thing, right? I don't have to do anything. It just like acquires that. And then interestingly enough, so it should also increment the top, but since we're updating the top, it should, yeah, so this entire thing sort of like we have release and acquire that cancels itself out, so we don't have to do anything in here. In case of a pop, this one is really, really interesting. So I take the frame, right, I take the frame, oh man, okay, so let me assign it back in here. So here's the frame, right, and essentially I will have to release the current top, right? So this is the index. Might as well call it something like top index, right? So this is the top index, right? I'm taking, yeah, so the first thing I probably want to do, I just want to release this thing. I'm completely releasing it. But it's kind of dangerous to do so, so probably not going to do that. I'm taking a frame. Oh man, my brain doesn't want to work. But the problem here is that I need to release the top index. Right, I'm releasing the top index. Is that a dangerous thing to do? I feel like it is kind of dangerous thing to do because it will set off the cascade effect. Right, so there's going to be 1, 1, 1, right, and you have this stop. You're releasing it right away. It sets it to 0, which releases that thing, which sets it to 0, which releases that thing, and so on and so forth. So it basically cascades. So we don't want to do that. All right, so that means we don't want to release it right away. First thing we want to do we want to grab the frame, right? So the current top frame, and we want to reassign the top to there, right? So we have a previous thing. I guess the first thing we want to do iter acquire, right? Acquire frame previous if it exists, right? That's what we want to do. So that's actually pretty cool. So this is a cool idea. This will not set off the cascade effect, right? So we have something like this, right? You have top in here. So instead of releasing the top, you grab this thing and you acquire it, making it 2, right? Then we're gonna move the top to here and we're gonna release the top, which will set it to 0, which will remove that thing and which will recommend 1 back here. So that will not set off a cascade effect, which will remove the entire thing, right? So you have to do that in a particular order. And this is why I was kind of scared of reference counting, because you see, you have to do that in a very particular order and you can set off something that you don't want to set off. But if you do that in the correct order, maybe it's going to be even easier than implementing mark and sweep. You see what I'm talking about? So yeah. And again, doing that in Rust adds a complication of borrow checker, right? Because now you have to also satisfy the borrow checker. I'm not sure like if I will be able to do that. So I need to take the frame, right? Here I'm actually, yeah, this one is interesting because here I'm borrowing iter, but to acquire the previous frame, I need to borrow it again. Right, so that means I have to borrow this entire thing for a brief moment and take the previous value. But this thing may not have a previous value, right? This thing may not have it. So let's actually set something like if let some previous index, right? So this is something that we want to have, right? So we take the top index, we unwrap it obviously, and then we take a previous. If it does exist, we have to acquire it. So we have to do iter acquire previous index. So we acquired that thing. Right. So after that, I need to do iter release the top index. So I'm releasing the top index, and then I'm setting the top to the previous one. This one is interesting, so I have to like do the separation yet again, right, which means that it would be better to actually save previous to here, like so, and then just set it like that. I think I did this shit in the correct order. That's right. So here no release acquire is required because you do a release acquire that cancel each other out, so you can just do that. Here you take the previous exists, you acquire that previous to not set off a cascade effect, and then you release the top and you assign the top to that. So all right, I think I did it. I think I actually did it. All right. So let me see. So we need to put a semicolon in here. Is it compiling? It seems to be compiling actually. All right. So I essentially just push some stuff onto the stack. Let's take a look at the SVG output. All right, so here is that, but we don't have a reference counter, right? Because we removed the reference counting. So let's go back to the reference counting. This one is going to be something like this, and the reference counting, ref count, ref, there we go. So let me see, there we go. So here are the reference counting, right? So it is in fact correct. We cannot see like the tops and stuff like that, but that's fine. We can just imagine them. Okay, so I also cloned this stack, and again, since I brought back the cloning, I need to have my own clone operation, right? I need to have my own clone operation. And let me quickly do that. So this is going to be mutable SelfAllocator, mutable FrameAllocator, and what are we going to do in here? SelfTop. If let some top index equal to that, right? That means what I have to do in here, I just need to acquire that top index, right? And then I can just return SelfTop, and that is basically it, right? So yeah, you just need to do another acquire in here. Okay, cool. But only if it exists, right? So anything else? So this requires a mutable eta. All right, cool. So you see, we cloned the stack, and now we have two things in here. That is cool. So now if I pop something from the first stack, right? That means now we're gonna have single pointer in here, but two reference counts in here, because yeah, you're gonna have first reference count from this node and the second one from the second stack, right? That makes sense, I think. I think that makes sense. Okay, so if I do that, there we go. So 2 moved down. And now if I push something to the first original stack, we have correct reference counts. Okay, that's cool. So we have correct reference counting. How about that? How about that? So we just have to do that in the correct order. So that's pretty pog. So we can push more stuff into here, right? Into the first stack. Into the first stack. So then, can we just go ahead and delete that stack? So the easiest way to delete that stack would be to just take stack top, unwrap it, and in the iter, just to release that top, right? That kind of makes stack 1 incorrect, right? But since we're using indices instead of references, the borrow checker is not going to tell us, but yeah. So essentially what this will do, it should remove this entire branch automatically, right? It should just like remove it. And I just want to see if it's going to happen. Okay, so I forgot to do this thing. All right. And it kind of worked, but this thing still exists, right? Okay, so this thing still exists, and this is because when it reached 0, did we actually free it? Okay, we didn't. All right. So what we forgot to do is to add this thing to the list of freed indices, right? So once the reference count reached 0, we have to add it to this thing, and then set of cascade effect. But maybe it makes sense to actually do that in here. Doesn't really matter? I don't think so. So there we go. And as you can see, this entire thing was removed. Right, so we removed one thing and it removed everything. So that's pretty cool. So we have a proper memory management based on reference counters and stuff like that. Isn't that cool? I think that's pretty cool. So it will be interesting to actually have like a more like better example. So maybe do something like a tree of some sort. I wonder if we can do that recursively somehow. Can we do that recursively? Just generate like random data types and whatnot. It would be also nice to have like a function that can generate a random data type. So if random type, right? And this thing will just return the data type. Oh, random number generators in Rust are like really fucking annoying. So the standard library doesn't even have a random number generator, right? I think it doesn't have a random number generator. Like it's a crate. It's a separate crate that you have to install. Okay. You think this is gonna stop me? I'm gonna just copy paste the LCG. Alright, so how do you do that? I keep forgetting. So essentially we have A and C, right, and we can have like some sort of a global seed. Might as well actually have like a struct rand. Right. So we have A and C, U64, B, C, U64. Right, we can implement rand. Method rand, which will accept a mutable self and will return a new thing. So it would be also nice to have some sort of a, like A and C usually are constants, right? So I'm not sure if I want to make them constant. Okay, let's actually make them constant. So it's going to be rand A. I don't know which one to put in here, so I'm going to put this one. B is going to be another one. So there's a couple of like good numbers in the Wikipedia, so maybe we're going to use them. So this is a seed, U64, and yeah, so that way we don't have to initialize anything. Right, so and the result is going to be the following, right? So we take rand A, multiply by self seed, right? So this is the current seed, plus rand C, and we just do mod on M, and M. So I don't remember. Let me see. And mod is usually, so okay, so the one that I use in Porth, mod is 64, that means you don't need mod at all, so we can just do something like this. Right, so, and we're gonna do self seed equal to that, and we're gonna just return self seed. Right, there we go. So we might as well even, like, one thing that I learned from using this LCG thingy, and one thing that people in comment section on my YouTube channel pointed out, is that you don't want to use the low 32 bits because they're like not really random. So you want to use the higher 32 bits. So the video I'm talking about is this one actually, right? So I really recommend to check it out. This is where I was using that specific LCG. So I'm going to put it in the chat for anyone who's interested, and also in the description. Right, so this is basically, I made the whole language just to generate this thumbnail. Okay, anyway, so let me see. And maybe because of that we want to return 32, and essentially we're going to return something like move it by, yeah, 32, right? So we're just basically removing 32 bits. And that way we can like have a random number generator. We can even like check the quality of this random number generator. So you see, you don't even need the right, the package or anything like that. So I think the main justification for not having random number generators in the standard library is that to prevent people accidentally using it in like cryptographic cases, right? So because usually these random number generators are not cryptographic, but we're not doing any cryptography right now, so it doesn't really matter, I think. So yeah, we just need to like generate some random stuff. So let's actually check how this entire thing works, right? So let's do for E in 10, right? I'm going to print ln. So we have to put something in here. So let's do it like this, 69. Can I just do it? There we go. It's going to be mutable, rand, rand. Cool. So this one is C. Okay, so let's set it like this. Anything else? So this thing wants a type, I think. Right, it wants a type. Right, and I think after that I have to explicitly cast it to U32. Right, is it fine? It should be fine now. Okay, so what is it complaining about? I'm not quite sure. So there's a bunch of warnings. Multiplication. Attempt to multiply with overflow, but isn't that what I want? Isn't that what I literally want? Can I just say, yeah, please overflow? So can I just like literally overflow? Overflow abs. Oh, you can actually explicitly do that. That's actually pretty cool. Overflow multiply. Overflowing. Okay. Cool. That's actually pretty cool. All right. Overflowing multiply. What a nice language. Can I have overflowing add as well? So overflow. Why do, like at this point, why do you even need an infix notation, Rust? If that's what you want your user to type out, maybe get rid of the infix notation and just like do all of the operations like this. That way you don't even need the traits for like add, multiply and stuff like that, because you won't have any infix operators, right? You can simplify your type system, you can simplify your standard library, you can simplify your parser, right? If that's what you want users to do, just like get rid of the infix notation. Come on. Okay, so oh, it even, okay, on top of that, it can also returns Boolean or something. You're fucking serious. Okay, so all right, so can be requires call expression requires. Okay, so that's what you want. Okay, cool. I generated a bunch of random numbers. Look at that. I have a bunch of random numbers. Okay, that's cool. So wrapping mode. Do I really want wrapping one? Maybe I do wrapping one. You're right. I think that's the one I want. Do they return Boolean? Thank God they don't return Boolean. Holy shit. Okay. And I have to pretend this is normal, right? So if I want to be like a good member of the Rust community, I have to like smile and pretend that this is absolutely normal. This is helping everyone. This is good, right? Do you understand? I think I understand that correctly. Okay. Right. So, okay. So cool. So what do we got? Yeah, all right. So what I want you to have is essentially just this thing. Rand. So we're gonna accept random type. All right. We're gonna take a mutable rand and we're gonna return the data type. And essentially, I'm gonna do rand 3. And can I just cast this entire thing to like to the data type as data type? Is that a thing I can do? Hopefully. As expression convert into primitive types. So Rust in number to enum. How do you do that? You can disable overflow checks in cargo.toml, but I don't use cargo. How am I supposed to do that? How am I supposed to do that if I don't use cargo? That's a very good question. So there's some traits and some other stuff. You know what? I really don't care, to be fair. I just want to get this shit done. Right, so... How more annoying do you want to make generating a bunch of random data for testing make? How more annoying do you have to make it? This is a very interesting question. You just have to make it annoying. You just have to. Right, so you cannot just like generate quickly. No, what if somebody's using that in a cryptographical context? You will get a vulnerability. No, you can't. Okay, so can I just do something like this? All right. Think about the children. Think about the children. What if the children will see your code, right? What if the children will see your random number generator and think that this is a cryptographic quality and will try to use that in their like security application or something like that? Anyway, so rand type is going to be mutable, rand. So I just want to see if I can simply generate this kind of thing. Right. All right. Okay. So stack 2, non-exhaustive pattern. Okay, so this one is going to be unreachable, right? Okay, so this is everything I wanted to do, really. Like, that's it. How hard could it be to just generate a bunch of random shit? Holy fucking shit. And again, according to the contract, I'm supposed to pretend that this is normal, everything's okay, it is helping everyone. Okay, so, cool. Yeah, I just want to generate a bunch of random data. So now we can try to do a recursive generator, right, that I suppose do the thing. So the idea is going to be the following, right? The idea is going to be the following. Generate tree. We're going to accept the stack, right? We're going to accept some sort of like a root stack or something. It's going to be stack and it's going to be mutable type stack, right? So in here, we're going to just push like a couple of nodes onto the stack, right? So for in 0, 3, right, so basically stack, push, we also have to pass the allocator, right, so it has to be something like eta, mute, what was that, FrameAllocator, right, FrameAllocator, there we go. So I push this thing here and I just want to have a random, and also you need to have this thing, right, so you need to have the random number generator and the allocator, and there you go. So here's the rand. You have a random type, so you just type a bunch of types. Oh my god, I'm so tired. Okay, so what do we have in here? So you just have to do it like that. Cool. Where is main? So I'm going to remove the main. This is going to be the new main. Generate the tree. So here, what I want to do, I want to split this entire thing like in two, right? I want to split this thing in two. Essentially, I'm gonna continue generating the tree to let stack 0 stack clone, right? And I'm gonna clone it in here, right? So something like this. Then I'm gonna continue execution on the previous stack. Might as well, yeah, that's fine. So it's gonna be random iter stack, and then on the stack 0. But we also need to keep track of the level, right? So let's introduce level useSize, and if level is equal to 0, we just return, right? So, and in here, every time we do a call, we decrement the level by 1, right? So we're going to have several levels in here. So we start with a specific stack, with the default stack, right? And I just want to generate a tree. So I also need to do something like rand seed 69. So there we go. And I generate tree. So I provide the random number generator, rand. Then I provide the allocator, hater, and then I provide this stack, right? So, and how many levels we want to generate? Let's say 3, right? So we're going to generate 3 levels. So that will basically just push some stuff into the stack, then it will split the stack and continue pushing, and it will just do that recursively and just to generate a bunch of stuff. Okay, so this thing, oh, this one is interesting. So I feel like maybe we have to pass this stack by the reference or something. So let me see. I might as well actually do it like that. It feels like I have to do it like that. Cannot borrow as mutable. It's not declared as mutable. Okay. So can I? All right. So let's take a look at the SVG. Are you guys ready? Are you guys ready? Boom. So here is the current situation with the stack. Right. So essentially we had a stack. So basically stack grows upwards, right? So we pushed a bunch of stuff, then we split it, and then continue pushing, and as you can see, yeah, there we go. So this is the persistent data structure. So, and at the end of the day, we just had 4 stacks, right? And they share some of the parts of each other. So, yeah. So, and all of the reference counting is actually correct in here, as far as you can see. We can increment the levels, right? So let's actually have 4 levels. So we have to be careful because it grows exponentially, right? So that's essentially what we have in here. And maybe we can even split it in 3, because why not? We can have something like stack 1 and stack 1 in here. So it's going to be a little bit more branchy, right? So as you can see, yeah, it just grows exponentially. So yeah, and as you can see here, the reference counting is working more or less correctly. So that's pretty POG, not gonna lie. Seems to be working. So and I can use this thing, I can use this setup. I can use this setup for Porth finally, right? Because at the beginning of the stream I said that for Porth I need some sort of like a memory management system and data structure, which will allow me to just clone these stacks, right? Quite easily and quite inexpensively, so I don't have to do too much of the memory management. And I think this thing suits that goal quite well, and I'm actually super happy. So yeah, really like that. Does anyone have any questions about what we've done so far? Okay. So, do I need to upload this anywhere? Because this is like a throwaway program that I don't really plan to do anything with, because I will need to translate this idea to Porth at some point. I just wanted to explore that idea on the stream. So all of that is going to be moved to Porth. Right, and in Porth we're going to have like a fixed arrays and stuff like that. I might actually upload that to Gist, right? So maybe somebody wants to play with this thing. Yeah, so I'm going to put it in the Gist. So how am I going to call it? Persistent stack rs. And I'm going to copy paste this entire thing. So I can't see shit in this mist, unfortunately. So let's create, do I want to create a secret one? Let's actually create a public one. So upload it to Pornhub. Does Pornhub even support like code or text information? Persistent. Did I make a typo? Where did I make a typo? Did I... Persistent... I understand. I didn't see a typo, I'm sorry. Anyway, so it doesn't really matter. So here is this thing, and I'm gonna put that in the description as well. Right, source code. All right, so that's it for today, I guess. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you next time. Thank you for all of the subscriptions, all of the donations and stuff like that. I hope this stream was interesting. It was definitely interesting for me. I never actually seriously used reference counting, and I can see that for this specific case, it is actually very, very useful. So yeah, okay. Thanks everyone for watching. I'm really tired, so I need to go eat something. Love you all.